Hey, do you believe yet that networks could be useful in your life? Well, they can, you know, in planning, staff, project management. And in this presentation, what we're going to do is have a look at a couple of other practical examples for the analysis of systems using networks. And have a look in the middle of the screen here. Here we have somebody watching the birds flying, and I think you've heard the expression, go as the crow flies. In other words, birds go straight from one point to another. They don't need roads. So over here, look at over here, we don't have to follow roads. If we're a bird, we go straight across as the bird flies, straight from S to F. Now, we've got all sorts of problems. We're not birds. We've got roads to travel on. We've got fuel and expenses to drive the vehicles we drive. So we want perhaps the optimal course, the shortest distance in our journey. And so over here is another diagram over on the right here. And it's indicating that if we're going from A to B, we want to plan out without backtracking perhaps. We don't want to go back on ourselves. That's going to cost fuel and time. So what's the best way of getting from A to B? It'll depend on the lengths of those roads, won't it? Let's do some of this analysis, because you can actually get a lot of value out of this in planning trips and in delivery patterns and so on for various goods. Okay, well, that's the idea. And down here, same sort of stuff again. If we're wiring a house and we've got a room which has a light in the centre of it, a power point on two walls, what's the best way of cabling that from the existing power supply so that it goes through a switch and also delivers power to those points within the house in the most economical and cheapest way in terms of cabling? Okay, and what about this trip over here? Want to go down to the southeast? From Adelaide down to Mount Gambier, a very picturesque area down that way. Which journey would you go? Which way would you go to get there in the quickest time, perhaps? So that's the sort of thing we're going to do. So let's get excited and have a look at what we're doing. So we're doing problem solving using networks. And the first thing we're going to do is to work out the number of paths that you can follow to get from maybe S here to F. And the algorithm, what's an algorithm? It's a method of solving a problem, method of solution. Can we come up with a method? And that's what we're going to do now in this presentation. Find a way of answering some of those practical problems. So what we're interested here in this first little bit of the presentation is we're interested in finding the total number of paths which go from one node, which could be a town or whatever, to another node without backtracking. So we're trying to keep it efficient. Remember we talked earlier about how networks can help you analyse a project or something in the most efficient way. Okay, so each connection on the graph allows traffic in one direction only, because we're not going to backtrack. Okay, we're going to go from S to F in the most efficient fashion. Okay, let's come down and have a look at how we might go about it. Here we have it. A to B. We want to get there. How many different ways can you go from A to B? Oh, well, you could start counting them up, couldn't you? Go from A up there, up there, up there, into B. We could go along here and up there. What is there a system? You could count them here mechanically for such a small network, but what if this was a much bigger network? Is there a system we can use to help us work out how many different paths there are possible in going from A to B? Let's have a look at the steps. So here's some steps from Hayes and Harris now. Publications. Step 1. So we're starting at our beginning point, and there are two possible nodes we can go to. So starting at the beginning, we could go to this node or this node. So there's one possible path to each of them, so we write one near each. So this one here means the number of ways of getting to that point, and that point from our starting point. You got it? Let's build it now. Okay, so our next step is to say, well, next step in the journey towards B, we want to go to B. What could we do? We go to the next node. So we're here, let's say at this one. Now, we could go the next step of the journey up to there, In other words, how many ways of getting there? It's still only one. But our next stage of the journey could be also to go there. Okay, and we could get there in two ways. There's one way of getting there, but to get here, there would be this way or this way. So there'd be a total of two ways, coming around there or coming around there. Do you get it? And the other part we can bounce off from this node, is this one. But that's overall only one journey, isn't it? So these two outside nodes have only one way of getting to them. This inside node you can come at from two different pathways. One path from below plus one path from the left. Okay, and we're going to do some funny business with these numbers in a minute. It's a good little system or algorithm for working out how many different pathways we can follow there. So let's have a look. So the final step is to repeat step 2 until we finish at B. So where are we? We've gone to there, or to there, or to there. Now let's do another node. Let's go to this node. Well, how many ways can you do it? Well, we've said you can come around there. That's one way. That's that number. And you could come from here, and there were two ways of getting to there. So the total ways of getting to this node is 3. So you write a 3 there. Okay, and we've been to here, so we want to go to this node. So how many ways can you get to that node? Well, we've said to get to here is 2 ways. Get to here is 1. So overall end up there is 3. So then to get to B, there were 3 pathways to get to that point, 3 to that, so you could have come around either way, so your total pathways are 6. So that's a nice little system, isn't it? Do you see how it works, how the algorithm is working? You, if you like, leapfrog from one node to another, accumulating or adding the number of paths each time as you develop from node to node. And when you're finally at your destination up here, then that number will be the sum of all the different possible paths. Mind you, it doesn't tell you the shortest one, does it? It doesn't tell you the shortest one. Let's come down here and look at the note from the book. I've added a little diagram here. If we must avoid a given node, start by putting a 0 at that node. And if we must pass through a particular node, start by avoiding nodes that do not allow passage through it. So let's say we have to go through here. We want to drop off some food or something to somebody, or just see friends. So we would not use this node, and we probably wouldn't use this node. What would we do? We'd go to here, and to here as before. This would be a 2, and we could then go to this node next. We're not going around there, so there would be 2 ways of getting there, and to here as well, 2 ways of getting there, so that would reduce to 4 ways, if you like. Okay, so we could do that sort of adjustment to our overall plan if we wanted to miss out on some towns or nodes or not go through them. All right, so are you getting the hang of it here now? Let's see if we can do some. So here's an example from the text there. Alvin, here he is, wishes to visit Barbara across town. Alvin's other friend Sally lives at the intersection. Find how many different pathways are possible in going from Alvin's place to Barbara's place. There are no restrictions. All right, so starting from A, here we are down here. Write numbers indicating the number of paths from the previous verses. So there's 1 way there, 1 way, 1 way. To get to here as before, you can come to that point or that point and come on. So that's 2. To get to this point, there's the outside way plus this 2 is 3. To get to here, you could go this 3 or that 1 is 4. And then to get to the next node there, that one, we've got to find these internal ones. So how many ways can you get to that point? You can come that way, that's 1. that 1 there and that 2 is 3. So, and you could come from to that point 3, so it's 6. So can you see how we're accumulating the different numbers of ways of getting to earlier nodes? Okay, so how many ways can you get to this node? Well, coming through all this to S, there was 6 and 4 is 10. Let's try to get to T. How many ways? Well, coming along here to get to there was 3, and to get to here and go up that way was another 1, so 3 and 1 is 4. How many ways can you get to P? Well, you're at T with 4 different ways, and S, I've messed it up, has got 6 different ways, so 6 and 4 is 10 to there. So how many ways can you get up to this node? There was 10 to get to there and 10 to here, so it's 20. Working out all the combos of ways. What about this node here? To get to there, how many ways was there getting to T? 4. One way of getting here, because it's just straight. It's the only way you can get to that point like that. So there's a total of 5. And what about this point here? Well, to get to P and come in that way, there were 10 ways getting to P, and there were 5 ways getting here, so 15 different ways of getting to that point. So there's a total of 20 ways of coming into B to that node, and 15 to this, giving a total of 35. Okay. Interesting, isn't it? Okay. Let's have a look at the next one here. The next one is going through S. So you see Sally on the way. What are we going to do? We must go through S. So we're probably going to drop out all the ones down here and up here, because they're sort of beyond the direction of S, if you know what I mean. Okay, so let's have a look. Let's do this. We're putting zeros there because they're off the track. Okay, so put those there first. Same stuff again. Starting at A, to get here is one way of getting there to get 1. Therefore, there's 2 different ways to come into here, 1 plus 1. Only one way still of getting up to there. How can you get to this node? It's 1 plus 2 is 3. And then let's look at the ways of getting here from the start. Only 1, but there's 2 ways of getting to that point, 1 of this one, so there's 3 different ways of coming in there. So S now, Sally's place, there's 3 ways of getting to that point, 3 to here, so you could come in from either direction with a total of 6 ways. We're not going to go down here, so all of that's out. So how many ways can you actually get to this point? Only in from this track, so that's 6 as well. How many ways of getting to this point? 6 of getting to Sally's, so that's 6, because we're not coming in this way. And then how many ways can you get to this point? Well, we weren't coming up here, so there's only the 6. There's 12 ways of getting there, and into this point, because it's just coming in from that angle, we're omitting this. Okay, so 6 and 12 is 18. A total number of ways of 18. Can you see the idea? Heading into the designated spot via various pathways. Okay, let's have a look at avoiding S. So this has got a 0 on it. I think I'd like to answer this one first before I do all this work. Can you see, if you must go through S, then you can say, well, it's the total number of paths minus the ones through S would be 17 that don't go through S. Let's see if we can work it out though. Starting at A, so it's 18, 35 take 18 is 17, is the answer. That's the answer to this dude's question here. All right, so coming up here, 1, to come to here, 1, same again, to get to there, 2, come to here, 1, so you can come into this point, 3 different ways as before. 1 to here to get to this point would be 4. We're not going to S, so we can't go that way, so let's come into this point. 1 to get to here, 2 to there, so a total of 3 ways for that point. And we're not going to go through S, so 1 way overall of getting there, 3 ways there, so 4 ways to get to that point. one straight way there and 4, so 5 ways to get to that point. How can you get to this point? You're not allowed to come in there, so it's just the 4 coming in that way. And same thing here, can't come from S, because not going there. It's 4 and 4. Get to this point is 8. And coming up here, 5 ways of getting there, coming in either way. 5 and 4 is 9 ways of getting there. So a total of 17 of coming in to B, omitting S. That's why we put a 0 at S. Okay, so just think of what we're doing. Try to get your head around it. Maths is fun if you can get up close and personal with it. And what we're doing here is saying we're just building up the pathways of getting to subsequent nodes coming in from different directions. Okay, your turn. I want you to have a go now. Get excited about this. This is just finding the number of different pathways. And we're assuming that backtracking is not allowed. We're not going to go back. Can't afford the petrol, mate. Can't afford the time. Got to keep heading in the right direction. Okay, so here's question 1 and 2. Have a go. I'll bring up the solutions in a minute. And question 3, I haven't shown here. You might go to your textbook if you've got it and look at the opening problem and use this technique to work out the total number of paths that you can go to from Gian's house to Van's house. Okay, let's have a look at the answers now. There they are. 7C1 from the textbook there. All right, that's good. Have a look. If you've got some wrong, go back and have a look at it and maybe check with your teacher. Let's go on. We want to do some useful stuff here. Shortest path problems. Yeah, you might have already asked, hey, why do you want to know the total number of ways of getting somewhere? Wouldn't you be really interested, come up here, to what's the shortest path? So shortest path problem is a problem where we must find the shortest path between one vertex or node and another in a network. Well, why might you want to do that? Well, if you're delivering food or some goods and you want to get through the towns in the shortest way, then, or the suburbs, whatever it might be, then you do need some shortest path system. Now in this presentation, what I'm going to do is I'm only going to give you one way of doing it initially, and that's basically by trial and error, just sussing it out. There is a string method that you can use, and then later on we're going to do a more complicated algorithmic method, a set method, so that for bigger problems you don't have to worry about trial and error. Anyway, here's our problem. Hang on, we've got to get rid of this. All right. So let's have a look now at this problem. Okay, it's trying to get from Adelaide to Mount Gambier in the shortest route. Well, I think it's pretty obvious that we're not going to go off on the side here down this way, I think. But we'd have to check the numbers, wouldn't we? I think we'll go 96, 130, 109, 101. Okay, this is maybe a more scenic route down the other side here. But I think this one is going to be shortest. So that's what we're going to do. And unless we had to, we wouldn't go through Robe. We wouldn't go off on that offshoot and in there unless we had to. All right, so let's have a look at doing problems like that now. So I want you to use trial and error and look at the lengths of the streets here and see if just by trial and error you can work out the shortest way to go. Okay, so adding those up and trying different ones. What would you do? Well, you try to use the shortest paths, wouldn't you? Try to avoid the longest distances. All right, see what you think. There's question 1. And there's question 2. I'll bring up the answers down the bottom, just poking their head up now. Okay, so here we are. Oh, they weren't distances, they were times. Yep. Okay. And these are prices here to get there. All right, okay. Getting the hang of it. It can be useful planning out your activity using networks. Let's have a look at the algorithm now. Dijkstra's shortest path algorithm. My pronunciation might not be that good here. But they had an interesting system so that you didn't have to go through trial and error and maybe miss out a possibility. There are stages in this algorithm or method of solution, but just remember, don't get frightened by that word. An algorithm is a method of solution. I don't like that there, it doesn't look good. Method of solution. So, what Dijkstra did, try to work out a way of not missing any possibility out. So we're going to go through this. You assign a value of 0 to the starting vertex or node. Draw a box around the vertex label and the 0 to show that the label is permanent. Because what we're going to do here is we're going to develop different numbers, different ways of getting to vertices, and then we're going to choose the shortest one later on. So you only box the one that's complete and found to be the shortest to that point, if you like. Okay, then you're going to go to the next vertices which are right next to it, connected to your vertex that you've just boxed, and go to the next one. And you label them with the minimum weight from the starting vertex. Oh, that means the minimum number of pathways getting there, if you like. And then you choose the least of all the unboxed labels and make it permanent by boxing it. So we'll have a look. We have to look at developing this. And then you keep going around the figure until you've looked at every vertex. Every vertex up to the destination vertex has been boxed. So this is a system so that you do not avoid or omit any vertices. Any. Okay. So that you know you've done the whole lot. Trial and error, it's easy to forget one, isn't it? So this is a system. You then backtrack from the end back through to find the shortest path. Let's have a look and see what we can do. We are trying to find the shortest path from a given vertex back to the starting vertex. Okay, and as you proceed, you get rid of the other shortest paths until you've got the one that wins, if you like. Let's do a problem now. We come down here, and here's our problem. Find the shortest path from A to E. We want to go from here to E. All right? And there's a few different ways of doing it. So first of all, you put in a 0 and box it, because that's not going to change. Now you go to the next node. So this is B and this is D. They are the next ones. And you label them with their distances, 4 and 3. Now, the smallest labelled one is 3, so you box it. Each time you move, the idea is to keep the number down. This would best be thought of as distances here, or time or something. So you box it when it's the winner at that stage. So the two nodes here that were considered together were adjacent to A. So there's one, and the other one up here, B. The winner was D because it was the shortest. So you boxed it. Okay, meaning you've looked at it, right? So this trial and error process is being refined here. Now, excuse me, consider the unboxed nodes connected to this one. So you've boxed it. Now which ones haven't been boxed? C and E. Okay, so we're going to think about D to C, and it's got a 2 there. So what are we going to do? We can label C with 3 plus 2 is 5. And D to E has a length 7, so we're going to label E with a number 10. Okay, now the next stage is to look at the smallest number again that hasn't been boxed. We leave the box ones alone. We're not going to go back and work out again, mate. So what ones have we got? Okay, I shouldn't have circled that. We've got C is a vertex and it's 5 and this one is 10. So the winner is, we'll box B at this stage, because we're going always to the next node to keep the distance or the time down. Okay. Let's have a look now at the unboxed nodes connected to B, because that was the last boxing. After the last boxing, we look at the next ones that are unboxed. So let's go from C. We've got C, we would have 4 plus 2 would be 6 to go there and there. But that's bigger than 5, so we leave 5 alone. If we go to E, we could go 4 plus 5 is 9, coming in this way from B. So we're going to call that a 9 now. Okay, so we're down to here. And, well, sorry, we've boxed C because that was the smallest one after our last box, which was B. Okay, now the unboxed, so the only unboxed node connected to C is E, and this is less than 9 here, so working this out, 5 and 3 is 8. So we've actually done all the vertices with a system, no omissions. So the trial and error thing is avoided. We couldn't make a mistake. Now the idea now is to backtrack through the network to find the shortest path. So we're going to start at E, E to C to D to A, go backwards now. So if we do that, A to D to C to E, so A to D to C to E, well, coming back from here, we said it was 8, we've got to find how it's 8. 3, 2 and 6. E to C to D to A. Coming back through this one, E to C to D to A. Well, I think we should put the arrows the other way. We're going to backtrack. So we're trying to find the way in which we got that 8. And that came from the 5 and the 3 in there. So let's get rid of that. So it came in this way. How do we get that number 8? You go backwards. So the overall forward path was A, D, C and E. Okay. Now, try to get your head around this. Don't just use the algorithm. Think about what you're doing. To get to each point, you're trying to find the minimum time or weighting or distance, whatever those numbers stand for in your particular problem. And when you get a little one, you say, I want that, and you box it. And you gradually move through the ones adjacent to it, boxing the smallest ones as they come up. If it isn't smaller coming in from a different way, you don't box it, and you don't count that number. Okay, do you get it? Let's have a look now, and we'll have a look at another example. What about we're forced to pass through B on the way to E? Okay, so hang on, what have we got here? A, and we've got to pass through B on the way to E. Okay, so here, let's have a look at what we're going to do. So what we could do, what's the length of the path, the shortest path from A to O? So here on the it's not on the way to E. Yeah, that's all right. Here, the shortest path from A to O. Okay. Sorry, I've messed this up here. I was reading that. It doesn't relate to this one. This goes back in the previous example. We've got to pass through B on the way to E. We'd split it into 2 paths, in other words. And we're going to do that example now. So we're going from A, so it's not on here at all. We're going from A to O, and we've got to pass through M down there. Okay, so let's look at the method. We find the shortest path from A to M. So we're going to do a mini problem in this section here. Okay, so we start at A, go to B, it's 2, and go to F, it's 1, so we'd box that. And then going on, it's 5, and here it's 2, so you'd box that next. Then going on, this is 3, so that's 5, this is 3, that'd be boxed next. Can you see the idea? To get these box numbers, you have a system. You box it when it's the smallest in the next step. So that would be boxed before L. And as we go on, we would have 6 and 3. So 3 there and 6 here. We're going to have a 6 at H. Okay, so you'd have to build these up, doing very briefly now. And to get into M, we would come in and have a 7 coming this way into there. Okay, so the H is a 6, not a 9 or not a 11, because we're coming in this way. And that's why we've boxed the 6 there. So you would have your shortest path there, which would be a total of 7, that score there. Okay, now to get the other path, we want to go from M to O. M to O, and we want that shortest length there, M to O. So here it's going to be a bit easier. It's 4 and 2 is 6, which is what we've got here going from M to O. You could have just seen that, or you could go around and look at all these adjacent nodes, but it's a little bit simple, that one. So your total distance is 13. Do you get the idea? So you can split pathways up into the shortest to a certain point, and then from that point onwards. All right, so you might go back and have a look at example 5. I confused that with example 6, but you could go back and have a look at that one. Let's have a look at trying to do some. Okay, remember the system. You start with a 0, you go to the adjacent nodes, and you box the one that's the shortest, so you keep boxing the short ones. Okay. Let's go on. Question 1, have a go. I'm going to show you question 2 now. And 3 and 4. Oh, I've left out that opening problem. Have to look at that in the textbook. So 2 and 3. Pause it, have a go. You might like to fast forward about now and see if you're getting them right. So you might have to go back and correct it if you're not sure. 5 and 6. Some different looking ones there. And they're coming down 7. Okay. So 7's an interesting one because it's getting very practical now. A salesman is based in one town and has to get to the other towns in the most economical way in airfares this time. So you need a network diagram. So this is starting a problem right from the beginning. This is a good use of network analysis now. So pause it. I'm going to show you the solutions now. Question 1 to 5. And questions 6 and 7. Now this is getting fairly heavy. We don't do much more of this, so if you found the last bit with the Dijkstra's theorem, algorithm, hard, don't worry too much in this course. This is built on a bit later on when you're a bit more au fait with some of the maths involved. Okay, well I hope you're getting a bit excited. There is a bit more to come with networking, with some more practical applications. So I'll catch you in the next presentation. Cheers for now.